Hi, this is Michael King, and we're talking about Debt Capital Markets Part 2. We're going to learn how to value bonds using the time value of money and what I call the magic formula, and then we'll look into the risk of different bonds, particularly credit risk and the role of credit ratings. The magic formula is the formula that I've shown you that can be used to value any security or asset. It has three main parts. You have to predict the cash flows that you will receive from holding the security. You have to predict the timing of those cash flows, and you have to predict the discount rate that you will use to find the present value of those cash flows. Once you find the present value of the future cash flows you will receive, that is the value of the asset. Let's take a look at how we can use this to value a bond. Now, a bond is quite straightforward to value because for a plain vanilla bond or a bullet bond, the coupon and the principal payments are known with certainty. We know the size of the coupon and the principal payments. We also know the date at which we will receive them. The only unknown is the discount rate that we're going to use to find the present value, and this is going to be called the yield to maturity. If you're given the price to the bond, you can back out what the yield to maturity will be, which is effectively the internal rate of return on this bond. You put up an investment up front that is a cash outflow, and you receive cash inflows in the forms of the coupons and the face value. To price a bond, you just need three things. You need to know the cash flows, you need to know when you receive them, and you need to know what discount rate to find the present value. Let's take a look at a bond issued by Bell Canada. The coupon was 3.25% with the maturity of June of 2020. At the time when I looked at this bond, the price was trading at 99.446% of par. So for a bond with $1,000 face value, you would pay $994.46. Because the price was below par, the bond was trading at a yield to maturity above par. And here you can see the yield was 3.35%. With any bond, you need to know who the issuer is, what the coupon is, and the frequency at which you'll be receiving it. Because this is a corporate bond, the coupon is paid semi-annually, and so you would take the coupon rate of 3.25, divide it by 2, and multiply it by 1,000. You need to know the maturity when you will receive your final payment, and you either need to know the price or the yield to maturity in order to calculate the other. Here we can see this same bond on Bloomberg. Notice that the bond is issued by Bell Canada. It has a semi-annual coupon, and the day count convention is actual days in the month and actual days in the year. The coupon is 3.25%. The bond has a par amount of $1,000, so multiplying by the coupon by the par amount will give you the size of the coupon payments in dollars. Bell Canada issued 1 billion Canadian dollars of bonds. The bond was rated Baa1, BBB+ by Moody's and S&P, making it an investment grade bond. Here on Bloomberg you can see the cash flows associated with the bond. Notice that you have semi-annual cash flows. Notice that you have semi-annual cash flows every June and December 17th. You can see the cash flows by taking the coupon, dividing it by 2, and multiplying it by the par value of the bond of $16.25 for each $1,000 bond. At maturity, you will receive the full amount, which is why this is called a bullet bond. Adding up the interest and the principal, you see the total cash flows that you'll use to discount to get the price today. So again, the discount rate for pricing a bond is called its yield to maturity. This is the return that you will earn if you hold the bond from now at the price at which you pay, and you collect the coupons and the face value. It is the internal rate of return on this investment. The yield to maturity is expressed as an annual rate, even though interest is paid and compounded at a semi-annual rate in this case. We take the discount rate and we double it to become the yield to maturity. So be careful when calculating this using Excel, because some of these rate functions may only show the periodic interest rate and not the bond equivalent yield, which is the annual yield to maturity. Now, different markets have different conventions, so bonds issued in Canada and the US, whether they're government or corporate bonds, may be quoted as an annual yield, but they pay interest semi-annually. Bonds issued in Europe and Japan, however, typically pay interest only once a year or annually. Be sure to adjust both the coupon that you will receive, the periodic cash flows, and the discount rate for the frequency of compounding. When you move into the bond markets, you will also have to make adjustments for different day count conventions, such as 3360, where every month is assumed to have 30 days and a year has 360 days, or actual, where you look at the actual days in the month and the actual days in the year, taking into account leap years. So when we look at this Bell Canada 3 1/4 due 2020, you can see that the price of the bond was 99.438% of par, or $994.38 for a $1,000 bond. The yield to maturity based on this is 3.35% approximately. Now the way bonds are traded is they're usually quoted as a spread over a risk-free rate. This bond is quoted against a 7-year Government of Canada bond, which had a yield of around 2.05%. As a result, the spread measured in basis points over this Government of Canada bond was 130 basis points. 130 basis points is 1.3%. Adding it to the 2.05% for the risk-free rate, you get the yield to maturity of 3.35%. Let's take a look at calculating the price given the yield and the coupons for a European bond. Here are the steps. You should draw out the cash flows that you will be receiving, both the amount that you will be paying up front, as well as the future cash flows that you will receive and when you will receive them. You need to calculate the individual cash flows. In this case, the bond pays a coupon of 5.375% every year, and based on a par value of one bond of 100 euros, you will receive 5 euros 0.375 cents. At maturity, you will also receive the face value of the bond back, which is 100. These are the cash flows. Next, you have to figure out your discount rate. The discount rate in this case is going to be the yield to maturity of 3.8%. Notice that the yield to maturity is below the coupon rate, so this bond is going to be trading at a premium or above par. With each of those discount rates, looking at the number of years, you would calculate what the discount factor is using your present value, future value formula. So for example, $1 received in 1 year at 3.8% is worth 96.34 cents today. You multiply the discount factors by the cash flows that you will receive in each period to find their present value. So the first payment of 5.375 euros is actually worth 5.18 euros today. Similarly, in the final period, year 6, you get the interest and the principal, and those two of 105.375 euros are going to be worth 84 euros and 25 cents today. Adding those cash flows up in today's dollars, we get the price of the bond today, which is 108.31 euros. Notice that the bond is trading at a premium because the yield to maturity is below the coupon. Let's try that again, except looking at a U.S. corporate bond that will have semi-annual compounding. Notice that this bond is 2 years, and so we'll have 4 coupon payments. Notice that the coupon is 5%, and so the semi-annual payment will be half of 5% times the face value, which will be $1,000, or $25. Notice also that the yield to maturity is below the coupon, which means the bond will be trading at a premium. So let's draw out our cash flows. We know that there are going to be 4 cash flows every 6 months. Interest payments are going to be $25. We know that at maturity we'll receive the $1,000 face value. The discount rate is going to be half of the yield to maturity because we're looking at semi-annual compounding. So we will take the 4% divided by the semi-annual rate to get 2% for each period. Calculating the present value factor, we will see that $1 received at the end of the first period, which is in 6 months, will be worth 98 cents today. Multiplying the discount factors times the cash flows, we get the present value of the cash flows. The $25 in 6 months is going to be worth $24.51 today, whereas the $1,025 received at the end of 2 years is worth $946.94 today. Adding it up, we get that the price of the bond is going to be $1,019.04, or it will be trading at a price of 101.9% of par. Here I'm showing you what it could look like if you were going to do this in Excel. Notice that you will have to be careful to use periods and not years when using Excel. You would set this up as a series of columns from left to right. Each row represents one period. Notice that you would set it up the way we described it. However, you could use formulas to calculate all the inputs, such as the coupons, the cash flows, the periodic interest rates, the discount factors, and the present values. Now you may be wondering, why would someone pay more than par for a bond? For example, why would you pay $1,019 for this $1,000 bond? Obviously, the person who is selling the bond is collecting a coupon that is 1% higher than what is currently being offered, and they want to be rewarded by receiving a higher price. So, if you looked at a new bond with a 4% coupon, it would be paying $20 every 6 months instead of $25. Let's look at what happens if you look at that difference in cash flow between the bond that pays $25 and the bond that would pay $20. You would have a difference in cash flow of $5 every period. If you were to discount the $5 every period using the 2% periodic factor or the 4% yield to maturity compounded semi-annually, you can see that the additional income that you will receive from holding this bond is $19. This explains why you would want to pay $1,019 if you were going to buy this bond. Just remember the price-yield relationship using this seesaw. A bond is poised over its coupon, and when the coupon and the yield to maturity are the same, we say the bond is trading at par. If the yield was to go down, the price goes up. And here you can see that a yield of 4% on a bond with a 5% coupon semi-annually for 2 years would generate a price of $1,019, or 101.9% of par. If the yield was to go up, however, to 6%, the price would fall down to $981.41 for a $1,000 bond. Let's look at this again using our Excel spreadsheet. Okay, remember that we can calculate the price of the bond by putting in the cash flows and using the correct discount rate, which is half of the yield to maturity. Here you can see that the $25 every 6 months plus the $1,000 discounted at 6% semi-annually generates a price of $981.41. The alternative would be to buy a bond currently that has a 6% coupon. 6% would pay $30 every period, not $25. As you can see, a new bond would pay you a higher coupon by $5 every 6 months. Now, while this may be $20 over the life of the bond, we need to look at it in terms of present value. Discounting each of those additional $5 at a discount rate of 3%, we would find a difference today of $18.59. That is the amount that the bond will be trading below par if you are willing to give up buying a 6% bond and buying a 5% bond instead. Notice that by buying a bond below par and having it mature at par, you are making up the difference over the life of the bond. Just be careful when using Excel to get either price or yield to maturity. You can use Excel's present value and rate functions. However, this only works for full periods, not for parts of periods. Remember that when you're using this in Excel to do the present value function, the amount that you pay up front is going to be a cash outflow and needs to be negative. The other cash flows that you're going to receive are positive. Excel does not know the difference between periods and years. All it knows is that there are going to be 4 cash flows that will be received. If you calculate the internal rate of return on those cash flows, it will tell you that the IRR is 2%. You have to double that, however, in order to get the bond equivalent yield, which is the yield to maturity. So, 2 times 2% will give you the correct yield to maturity of 4%.